Hi, Assalamualaikum to Dr. Nordin and to those who are watching this. My name is Muhammad Arif bin Yaakob. My ID number is 204692 and this is presentation for static EMM3103. So for today, I'll be covering these four topics. The first one is basic concept in statics. The second one is force systems. The third one is equilibrium, and the last one is analysis of friction in bodies and structures under static conditions. For the first topic, these are the basic concepts in statics. We have length, time, mass, force, particle, rigid body, weight, and Newton's law. Right now we already know most of them, so I'll cover only three of them, which are particle, rigid body, and Newton's law. So a particle has a mass, but a size that can be neglected. The geometry is simplified and does not involve in analysis of the problem. For a rigid body, it is a combination of a large number of particles with a fixed distance from one another. And the deformation in the structure or a body has to be small in order for rigid body assumption to be used. So, Newton's three laws of motion. We have three laws: the first law, second law, and third law. The first law states that a particle originally at rest or moving at constant velocity will remain in this state provided that there is no subjected force to this particle. And for the second law, the equation we're familiar with is F equal to ma, and it states that a particle experiences an acceleration that has the same direction as the force and a magnitude that is directly proportional to the force. And for the third law, the mutual forces of action and reaction between two particles are equal, opposite, and collinear. For Newton's law of gravitational attraction, we'll be using this equation: F equal to G m1 m2 over r square. The definition for this law is that the every object in the universe, considered this particle m1 and m2, they attract each other with a force directed along the line of centers for the two objects and proportional to the product of their masses, and inversely proportional to the square of the separation between the two objects. So that defines these equations. Next, for the force system, we already know what vector is. Vector differs from scalar with the addition of direction rather than magnitude only. So a vector can connect 2 points. A vector can connect 2 points in space. This one. Let's say this vector is vector A, and having the vector go the other way is considered negative vector A. In 3D space, Cartesian coordinate system use ijk. Note that the vectors ijk are the unit vectors along each corresponding axis. So negative I refers to the opposite side of I, which is here. Negative K refers to this side, and negative J refers to this side. So let's say this is vector A. Vector A can be broken down into its components along each axis. These three axes: AX, AY, and AZ. And these components are what making up vector A. Then vector A can be expressed as AXI plus AYJ plus AZK. And if we use Pythagoras theorem, we can get the magnitude of vector A. And in order to find the value of AX, AY, or AZ, we can use basic trigonometry. if we were given the angle of the vector itself. So what if we have more than one vector? If we have more than one vector, then we can add up all these vectors. The easiest step to do this is by graphical solution. This will yield a closed polygon like this one. Vector A plus vector B equal to vector C. Any arrangement would yield the same resultant vector. Let's say we'll take the same example and we draw it this way. The vector A here, and then vector B here, and the resultant is gonna be the same as the first one. However, if one of the vector is a negative vector, then the resultant vector won't be the same. I will show you here. If we have vector A here, and then we have negative vector B, is the opposite way of the vector B we have here. Then if we reconstruct it, vector A here, vector negative B here, and then we're gonna get the resultant vector here, and this is not the same as the first example. So when all of the forces acting on a body are balanced, then the system is said to be in a state of equilibrium, where all forces are balanced with each other. So if an object is in equilibrium, then all of the forces and moments are balanced. For particle equilibrium, moments are not involved due to the particle's small size, and therefore the geometry can be neglected in the calculation. However, for rigid body, since it is a combination of particles and the shape is relatively bigger, rigid body equilibrium needs both force vectors and moments, and both of these parameters need to be equal to 0 in order to be balanced and in equilibrium. So here is the particle equilibrium example. There are two forces, F1 and F2, both are the same magnitude and acting on a particle, and both are on opposite side. Therefore, the particle is in a state of equilibrium. It is static and not moving. If more forces acted on this particle, then we'll be using the previous method. We will use graphical solution to yield a closed polygon, and after that we can then do the calculation, the summation of fx equal to 0 and the summation of fy equal to 0, and we'll be using Pythagoras theorem to get the resultant force of the vector. So for the rigid body, in contrast to the forces on a particle, this one, the forces on a rigid body are not usually concurrent and may cause rotation of the body due to the moments created by the forces. Then for a rigid body to be in equilibrium, the net force as well as the net moment about point O must be equal to 0. The moment vector m for a force about this point is the cross product of the force F and the vector from the point O to the point of application of the force given by the position vector R, this one. So in vector format, the moment is given by a vector cross product here, and in the cross product or vector product of two vectors may be expressed as this one. Analysis of friction in bodies and structures under static. Friction is a force that always resists motion and impending motion. It acts in parallel to the surface with which an object is in contact with, and frictional force exerted on a stationary body is known as static friction. If the body is moving, then the friction is known as dynamic or kinetic friction. Dynamic friction for a given body is less than static friction on the same body, and the magnitude of the frictional force depends on the normal force and the coefficient of friction between the object and the surface that it is touching. So let's take this example. For a body resting on a horizontal surface, the normal force is the object's weight because there is no other force acting on it and the object is in equilibrium, in static. So we have N, the normal, equal to weight equal to mg. So N equal to mg. Okay, suppose now that the horizontal force P is applied to the block, then if P is small, the block will not move. There is a reactionary force F that pushes in this side the opposite direction of P to counteract the force P. This force F is actually depends on the normal force N and the coefficient of static friction. We need to use this equation F equal to nu S times N, where nu S is the coefficient of the static friction and N is the normal. So if the body is on an inclined surface like this one, then the normal force become W cos theta, and since W is equal to mg, we have normal equal to mg cos theta. And for the frictional force, it is given by nu N. Since N equal to this one, then we have nu mg cos theta. This thing is simple because if we use basic trigonometry, we can get these equations. And since we are dealing with static analysis, we have the information that the coefficient of static friction is greater than the coefficient of kinetic friction. Nu S equal to nu K. And if you're dealing with kinetic movement, or we have motion for the block, then the nu K is greater than the nu S. And that's all from me. Thank you and stay safe. Bye.